Well, you know what? Recently, we've had quite a few unfortunate scenes that, despite their Bollywood cheesery, have turned out to be theoretically possible.
This is an outrage.
You know, what we need now is a win. We need a sure thing, a hole-in-one.
We need a helicarrier.
So, here's last summer's biggest blockbuster, the Avengers, and their insane mode of transportation, the Shield Helicarrier.
Because nothing says shark-jumping balderdash like a flying unicorn filled with semen.
So, what we were trying to figure out here is where in the world these rotors came from. I mean, do they stay under the ocean all the time or what? Because that would be the biggest drag ever while they're under the water.
I mean, this is the kind of crap they come up with in comic books, not Hollywood.
Yeah, I mean, look at this. Not only are they lifting the carrier, but probably about 1 million gallons of water along with it.
Plus the aircraft, the personnel, etc., etc.
Exactly. I think even Michael Bay knows better than this.
You know what? Hollywood should make a movie about something like this. You know, like a battleship.
Alright, so here's how we're going to approach this. First, based on an estimate of the size of the helicarrier and its rotors, we're going to calculate the thrust generatable by its 4 lifting units.
Right, and then we're going to compare that force to the weight of an actual carrier, and then by making some material substitutions, we're going to compare that to a hypothetical aluminum or carbon fiber helicarrier.
Okay, well first, let's look at some helicopters.
Helicopters are big fans in the sky. I mean, really, they are, which when you think about it is really astounding, like when you realize milk comes from a cow gland.
Right, so they rely on taking air that is just floating around and accelerating it downward to create thrust.
I mean, think of all the movie scenes that would not be possible if Paul Carnew had not had the gall to make a flying freaking fan.
Now, let's look at thrust. There are 2 ways to approach rotor thrust.
One is momentum theory, which looks at the change in the velocity of the air that the rotor is moving, and the other one is blade element theory, and we're going to use that one.
Right, in blade element theory, we treat each blade as a wing.
Great, let's do some math.
Alright, the thrust generated by each blade is given by this formula, where T is thrust, C sub R is the thrust coefficient, F is the swept area of the blade, Rho is air density, and V is the airspeed velocity at the tip of the blade.
Everything in this equation can be looked up, estimated, or calculated, except for the C sub R. C sub R is a unitless number that is a function of the rotor shape and angle of attack, and for helicopters this is typically between 0.008 and 0.01.
Right, so we are going to fall between those 2 values and use 0.009.
Seems legit.
Okay, now comparing the pictures of a Nimitz-class carrier to the Shield Helicarrier, and using the 16-meter rotor size of a UH-60, plus the 9-meter wingspan of real jets, we can get the scale of the helicarrier.
Now, since the helicarrier has a large hub in the center of the rotors, we are going to subtract that hub from the swept area.
Okay, so now we need to get that swept area, which is calculated here on screen.
That comes out to 1,809 square meters per blade. It appears that there are 18 blades per fan, 2 fans per nacelle, and 4 nacelles. So the total swept area, F sub T, is 260,000 square. Oh my god, that's a lot of area. Wow!
Man, okay, so now let's figure out the tip speed.
Okay, for sure the tip speed has to be less than the speed of sound. And we're guessing that at hover, the tip speed is going to be that of around a Black Hawk.
Right, so let's figure out the tip speed of a UH-60 Black Hawk helicopter to get a ballpark velocity.
Right. The angular velocity of a UH-60 rotor is 26 radians per second. The radius of a UH-60 rotor is 8 meters, so the diameter is 16 meters, just for reference.
Right, okay, so the velocity of a point rotating about an axis is angular velocity times the radius. So, the tip velocity of a UH-60 rotor is 475 miles per hour, or 765 kilometers per hour.
So now using that tip speed as a basis, we can find the thrust of one of the helicarrier rotors. Now let's go back to our original equation.
Using that equation, it comes out to 64,143 kilonewtons.
Now that's a lot of thrust, like 14.4 million pounds or 6.5 million kilograms of force.
Okay, so what are we lifting here? I mean, what is the mass of a Nimitz-class carrier?
Okay, a Nimitz-class carrier is 100,000 tons, which is about 9 million kilograms, which exerts a force of 889 kilonewtons.
Okay, so let me get this straight. All right, our 4 rotors create a thrust of 64,000 kilonewtons, and we're trying to lift a carrier that's actually larger than a Nimitz-class carrier that already exerts a force of 889,000 kilonewtons.
Right, it's done. Done deal. This
All
is
right,
real
hold
physics.
on, hold
See
on,
you
hold
next
on,
week.
hold on. No. What if we made the Helicarrier out of aluminum?
Okay, let's take a look. No, that doesn't work either. The density ratio of aluminum to steel is 0.35. So even if you made the whole damn thing out of aluminum, which by the way you have to use more of because it's actually more flexible than steel, you still have to lift 307,000 kilonewtons, which is way more thrust than you have.
All right, okay. But let's go even crazier here. What about carbon fiber?
Okay, so let's say you made the whole damn thing out of carbon fiber. The density ratio of carbon fiber to steel is 0.22, which is not that much better than aluminum. So a carbon fiber helicarrier would still weigh 201,000 kilonewtons, which is still more thrust than you have. And remember, that's with 8 18-bladed rotors.
All right, well, let's go ahead and call it.
Okay, this is one comic that won't stand up. This is real physics.
There you have it. And you know what? We didn't even have to calculate the weight of Thor's hammer.
Or the thermal coefficient of Scarlet's hotness.
Until next time, thanks for watching.
See you next week. Yeah,
the last one before this was real, but the one before that was real.
Okay.
And then the one before that was real.
So the total swept area, don't move your hand. You're gonna do it again, aren't you?
I'm not.
So a Helicarrier.
Helicarrier. A Helicarrier. Okay. All right, now let's look at thrust. Okay. See, that's not even me. That's not who I am. You have a UH-60 Blackhawk and get a velocity ballpark. Wait.
I'm not gonna laugh at that. That's worse than airspeed velocity. Okay.
Who are you, Dolphin Lundgren? Did you say a hoe efficient?
That's what I keep trying to tell you. It's a hoe efficient.